So we're working our way through the algebra part of this course. And of course, we just finished talking about systems and quite a bit of application. We're now going to move into a unit on solving equations. Now, it might sound like that's what we're always doing, but really we're going to be solving some specialized equations, some that you'll recognize from some prior algebra, but I'm sure that some that'll seem new and no doubt that we'll need to brush up on anyway. So for this unit on solving equations, the first kind of equation we're going to solve involves, well, let's find out. We've got ourselves another little scratch off here. It's going to involve using, would you like to buy an F? Sure, let's buy an F. Would you like to buy a T? Yeah, let's buy a T. I got to make sure that I'm not missing one. Do you know what word it is yet? You might if you recognize it from yesterday's word splash. We're going to be using, at least in this first topic, we're going to be using the fundamental, I forgot a T in there, fundamental theorem. We're going to use the fundamental theorem to solve polynomial equations. Now, no doubt you have some knowledge of polynomial equations, and you showed that by your response to the word splash from last night. And I like the answers that were given. In fact, some of the answers that were given described that people said that you can use the quadratic formula to solve, well, of course, a quadratic equation. Some of you actually wrote the quadratic formula. How about imaginary roots? A common answer was that imaginary roots will involve the letter I. That's correct. Do you remember what I squared equals? That's right. I squared equals -1. What's one other good one here? Somebody wrote, they wrote in all honesty that they're not sure how to complete the square, but they know that it has some connection to basically the fundamental theorem, which is true, but no doubt completing the square is going to be a pretty specialized method that we study. I'm excited to do that with you shortly. So here's one other good one that was written. This was pretty specific, but a student described the end behavior of a graph as the behavior to infinity. And maybe you had a teacher that did a little dance with you where the end behavior might be going up, might be going down, might be going up, up, might be going down, down. And I'm not much of a dancer. But yes, end behavior has to do with what happens as you go to infinity, of course, meaning as x goes to infinity. Well, let's jump into the fundamental theorem. Exactly what is it, and how can we use it to investigate a polynomial? You know, it's important that you realize that a polynomial isn't just any old equation. Polynomial equations have to be such that we have one variable. They have exponents and terms. Not every equation has one variable, exponents, and terms. You know, like the trig functions, sine of x or cosine of x, they're not polynomial functions. And I'll fill you in a little secret. In a few weeks, we'll be talking about rational functions, which are fraction functions. There's no fractions in a polynomial. So polynomial functions are kind of their own breed. But of course, when we start looking at them, we have all kinds of interesting connections. And one of them is going to be the fundamental theorem. Now, here's p of x, x to the third, plus 3x squared minus 4x. And what we want to do is we want to consider, which is the most common thing to do, we want to consider the root, the 0, or the x-intercept of p of x. And we note that they will all make the p of x equal 0. So we have this idea that a root, a 0, or an x-intercept, they're all interchangeable, will make the polynomial equal 0. Exactly what does that mean? Well, let's take a look with a simple question. Is x equals 1 a root? is x equals 1 a root? We'll make that a little question. The most fundamental way to discover or to decide is to plug it in, because as it says, x equals 1, and of course that means that we can substitute the number 1 in for x. Now what I'm going over here is pretty basic, but it turns out it's the one thing that students seem to forget. So let's remember now that, well, you can plug in. And when you plug into this polynomial, you get 1 cubed, which is 1. You get 1 squared, which is 1, times 3, which is 3. And then, of course, minus 4. And if you keep following the order of operations, you end up with a big old 0. So yes, x equals 1 is a root. But what else does that mean if x equals 1 is a root? It seems to imply that it would mean something about the graph of p of x. Now, I encourage you to graph this on your calculator, although I'm going to show you a graph in just a second. But if you want to pause and graph this on your calculator, do you know what to expect? Are you surprised when you see a function that has an x-intercept of 1? Well, I'd like to say that you shouldn't be too surprised, because we just got done saying that 1 was a root. And of course, that's the same as an x-intercept. By the way, I changed my window just a little bit in case your graph looks different than mine. But your eyes should be drawn very quickly to what appears to be some other x-intercepts, which of course means some other roots. Yes, it looks like x equals 0 is an x-intercept, which means it's a root. And it looks like x equals negative 4 is a root. And so, yeah, we actually end up with a greater list of roots here. Call it 1, 0, and negative 4. Now, call me a math teacher, but I think I'm counting 3 roots, right? There's clearly 3 roots. Is that just coincidence? Indeed not. You see, we might have been able to argue that we already should have known that there were 3 roots. Why? Do you remember what part of the polynomial screams to us 3 roots? Are you looking at the degree of 3? Now remember, degree is a fancy word for the highest exponent. But you see, the degree of your polynomial will always determine the number of roots. And that, ladies and gentlemen, is the fundamental theorem. Now, the fundamental theorem says that every polynomial of degree n is going to have exactly n roots. In other words, the highest exponent will determine the number of roots in your function. Sound familiar? Okay, it's a pretty major idea. In fact, in mathematics, the interesting thing in mathematics is that there's a couple fundamental theorems. Actually, in calculus, my students are going to discover also today what's known as the fundamental theorem of calculus. And it's kind of like what the whole subject is built upon. And so in algebra, everything's built upon the degree. Now, we solved this problem by looking at a graph. We also kind of plugged in a number. But what if I just wanted to find those answers by using my equation, kind of some good old algebra? Well, remember that you can certainly factor. You can certainly factor to find your roots. And when you look at this polynomial, it's not meant to be that part of a factoring. Factoring doesn't have to be a bad word. We're just going to factor out a GCF. So we pull out an x. And I hope that you feel like you want to keep factoring because we have a trinomial. And of course, you're just looking for the right combination of numbers. They just have to multiply to be negative 4 and add to be 3. That's because the coefficient is 1 on this polynomial. So pretty quickly we arrive at x plus 4 and x minus 1, right? Those two numbers multiply to be negative 4 but add to be 3. And remember that each one of these factors is going to contain the root, or as we sometimes now call the 0, because of course those 3 red numbers will make the equation equal 0. And that is a little bit of a spin-off of the fundamental theorem, because the fundamental theorem also then would agree that every time you have a root, call it r, you will have a factor that goes with it, and we'll call that x minus r. Coming back to you a little bit, why don't we take a look at another example of a polynomial that purposely is going to have some different ideas that we can discuss. Here we have p of x equals x to the fourth minus 81. And yep, I did it. I gave you imaginary root. X equals 3i. That's an imaginary root, but is it, or I should say, is it going to actually be a root? Let's find out. Let's plug it into this polynomial. Now, when I plug in 3i, I'm going to be plugging in for x. Okay, so of course that does mean that it's going to be x to the fourth power. Let's talk about that a little bit. That's really the purpose of this problem. Now, it doesn't hurt sometimes to go back to the basics, which would be to essentially expand the 3i to the fourth power to be what it represents. 4 of those 3i's multiplied together. Now, I'm doing this because if I put them in groups of 2, I end up with a significant math value. Now, it's going to be 9i squared, but does that I squared kind of ring some bells to you? I squared. Well, I squared, it's a math fact, is always equal to -1. Now, since I squared is equal to -1, then we're really staring at a couple -9's being multiplied together. And, it looks like that even though I had an imaginary root, that when I do the math, I end up with a big old 0. And so imaginary numbers, they can be roots. They can actually make an equation equal 0. But I feel like we got some work to do here. You know, let's be honest. There's supposed to be 4 roots to this problem, right? I only have 1. So, like, where's the other roots? And how are we going to find them? Let's use this factoring approach. Okay, even though it was the last thing that we did in the other problem, there's no reason it can't be the next thing we do in this problem. Now, x to the fourth minus 81 is an interesting polynomial because, well, first of all, it's kind of perfect. You should feel like the numbers are squares. In fact, because there's a subtraction sign, we have a difference of squares. Anytime you have a difference of squares, you can always factor it into 2 binomials that contain, well, I don't want to say the same terms, but that both contain the same looking terms with a plus and minus. We call it a sum and difference. Now, the reason I could do this is because it was a difference of squares. X to the fourth minus 81 is a difference of squares. And it always factors into a sum and difference. Now, if you're looking at this carefully, you should feel like that there's another difference of squares, isn't there? That's right, x squared minus 9 is another difference of squares. How do you factor a difference of squares? Into a sum and difference. A sum and difference just means that you're going to have 2 binomials that aren't the same, but they contain the same terms with a sum and difference. Now, I'm telling you, probably one of the most common mistakes with factoring is that students want to try to factor x squared plus 9. And maybe I should have showed here that that's a no-no for a number of reasons. If you try to factor it with a plus 3 and a plus 3, it's a nice try, but that's not going to produce the x squared plus 9 because you're going to get an extra 6x. So that's a no. And of course, if you factor it as a sum and difference, well, then you're not going to get x squared plus 9. So it turns out that you can't factor a sum of squares. You just let that sum of squares be x squared plus 9. All right, why are we doing this? Well, to solve it, right? To solve it for the zeros or the roots, as you prefer. But, oh, look, I have a couple more roots. I have a plus or minus 3. And then I have an interesting observation with my x squared plus 9. You see my x squared plus 9 right here, it also wants to equal 0. And if I carefully go through the algebra to make that equal 0, just a little subtract 9 from both sides, it turns out that, well, that every time you're going to end up with the square root of a negative number. Now, we got some stuff to remember. First of all, when you take the square root of anything, you always get plus or minus. Secondly, because it's a negative number, I'm going to end up with an imaginary result. So I'm going to get plus or minus an I. And, well, the square root of 9 evenly works out to be 3. So we call it plus or minus 3i. Now, you should say that you've seen this before. That is, that you've seen 3i. It turns out that its buddy just needed to come along, the negative 3i. And this is always the case when you have imaginary numbers. Imaginary numbers will always come in a pair. We actually call it a conjugate pair. Conjugate's just a fancy word for the plus or minus. So, I think I have my 4 roots. So the fundamental theorem has been satisfied. Of course, it's always satisfied, and everybody's happy. Except for the graph. The graph's not super happy because, well, it doesn't really say it all. But if we listen carefully, we understand that it says what it can. And it says that the real roots are going to always show up on the graph. The real roots are always going to show up on the graph. But the imaginary roots, well, they just can't, because this is a real graph. By the way, just some other things that are helpful. The y-intercept shows up on the graph. Although that doesn't necessarily relate to the roots, it's just something that we can observe. So what happened in this problem? What happened? I should mention that the graph that I have shown here, if you're graphing it on your own calculator, I did significantly change the window. I made the y window drop the whole way down to negative 100. Okay, that way I can kind of see the bottom of the graph. Imaginary stuff happened here. Let's make sure that we're good with these conclusions. Imaginary roots, they always come in plus or minus conjugate pairs. So that was my plus or minus 3i. That's a conjugate. Okay, and again, I promise, basically, if you're going to have 3i, that means you were going to have negative 3i. And then, of course, these imaginary roots, they don't show up on the graph. Okay, I don't want you saying something silly like that they also are these points. These points, remember, those were the real roots. Is it coming back to you? Let's do one more thing in this initial day. I like to cover a number of topics, and essentially what we're going to do is we're going to do this backwards. If I give you some roots, can you write the function? Can you write the polynomial function? Okay, well, in order to do this, we do have to go back to a fact that was on a previous slide. It doesn't hurt to remember that basically you're going to use this factor fact. We'll call it a factor fact. That is that x minus r will always be the factor that matches with a root that's equal to r. So we're basically going to match these, these roots. So what do we have here? We have x minus 2. I'm going to match that with a factor. I hope that you would match that with x plus 2. Yes, I have another root, or I should say I have the same root again. Now, this is something significant that in our next lesson we will review, but I just want to mention that it's not a mistake. I've had the same root written twice. So I have to have this factor written twice. And then I have this imaginary root here, this 2i. Now that seems funny. It's just kind of sitting there by itself. Yeah, it's strange, right? Whenever you have an imaginary root, it always comes with a pair. And so this was just meant for us to realize that if I tell you that 2i is a root, then you can know that negative 2i is a root. You always have them together. Now, I don't know about you, but I don't want to write down a silly factor like x plus 2i. Instead, what I want to do is I want to think about where 2i and negative 2i came from. And, well, they always come from a sum They always come from a sum of some type of x squared. And then in this case, we just have to think a little backwards with 2i originating from a 4. But I'm telling you, this plus sign right here is pretty important, because that plus sign is what's going to give me the imaginary part of this answer. Okay, you need to multiply these out. It's just kind of a given that when you're asked to write a polynomial, that you want to write it in standard form. So I'm going to choose to group those first two together. Why not? It's easy to multiply x plus 2 times x plus 2. Of course, that's x squared plus 4x plus 4. And then remember that the x squared plus 4 is just waiting to come on in. So it's knocking, let's let it in. And students do this different ways. Some people will kind of think about doing the distributive property. Ain't nothing wrong with that. You can do the distributive property. I'm going to change the color here a little bit. When I do that distributive property, I get x to the 4th, I get a 4x to the 3rd, and a 4x squared. And then don't forget to do the distributive property with the other term. So I'm going to get a 4x squared. Now you'll notice I'm doing something here. I'm sort of lining up my like terms. So I'm going to line up my 4x squareds. And I still get a 16x and a 16. Yeah, so I don't know why something looks funny here, but I believe that we're good. So we'll just come up with our final answer here of x to the 4th, 4x cubed, 8x squared, and the 16x and 16. Okay, so there's our polynomial function that contain those roots. Now, next time that we gather, we will dig a little bit deeper into the graph of these polynomials. In fact, we'll actually dig a little bit deeper into a few more of the terms that are in this word splash. But I hope right now that you feel like that you've had a refresher on the fundamental theorem. We talked about real roots and factors. We don't want to cross that out. X-intercepts. We even had some imaginary roots. We even used the word degree. Okay, but just to get you thinking about this word multiplicity. Yeah, it was in the previous problem that we just did. And we even get some discussion on end behavior. Okay, but that'll be for the next time that we get together. This time, spend a little bit of time refreshing on some polynomial basics, on some homework on page 109, and we'll see you back here next time.